Again, welcome and thank you for joining us in this month's webinar and helping us kick off the new year. Today we have Dr. Oliver Kreylos. Today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and the presenter will have their microphones enabled, so use the chat window or type in your questions or to communicate with others. Presentations in this series will be approximately 50 minutes in length, with questions and answers following during the remaining time. There's also a slight delay in the audio and video feed, so please be patient. Today's talk is the first of two talks this year on visualization. Today's talk is by Oliver Kreylos. Oliver received his PhD at UC Davis and is currently a researcher with and chief architect of the KeckCAVES at UC Davis. KeckCAVES provides a 3D immersive environment for researchers to interact with their data in real time. Under his leadership, projects in the KeckCAVES have won a DOE geothermal energy competition for the visualization of the Valles Caldera region in New Mexico, been used to visualize and map the surface of Mars, study the dynamics of the Earth's interior, and are used for archaeological preservation. He has developed low-cost virtual reality systems in use for science, outreach, and education, and an augmented reality sandbox in use by science museums across the country. His YouTube channel recently reached 7 million views. Today, he explores with us the power of 3D visualization.
Well, hello everyone. I hope you can hear me. This is the first time I'm doing a webinar or listening to one, so I don't really know how this works. I guess we'll see. 15 minutes is a bit short for me. I normally do longer things, so we'll see how it goes. As Lorraine already mentioned, I want to talk today about interactive visualization and specifically for scientific data analysis. The title kind of gives it away. So to get started, let's just make sure that we're all on the same. Okay, that didn't work. Go to the next page. Hang on a moment. Here we go. Just to make sure that we're all on the same page. When I say visualization, I'm specifically referring to the process of turning data into pictures. So if you're here to learn about how to stop smoking using visualization, wrong webinar. When I say interactive, what I mean is that we're not looking at static pictures, like you do a printout and you look at that like a chart, but that we're manipulating those pictures in order to learn more about the data. And especially we manipulate them with real-time feedback. That's a very important part. If you do something and the result comes up a minute later, that's not good enough for this. And so then scientific data analysis is the process of using pictures, using visualization in this case, to extract information from data. So the questions we are asking here are things like what features are in the data, where are those features, how big are they, and so forth. To give an example from the medical area where we do a little bit of work, if your data set is an MRI scan of some patient, then the kind of question that you would be asking is there a tumor or not, where is it, how big is it? So that's the kind of derived information that we want to get out of it, which is of course a much smaller size than the original data. Might just be a yes/no answer. All right. Now, one thing that I didn't mention in the title is, of course, that when I talk about scientific visualization here, I specifically talk about 3D data visualization. I'm not really that interested in 2D data visualization, which is, as it turns out, a much, much simpler problem. I don't want to go over all the details here, just to mention it briefly. The source data we are looking at are conceptually functions f of x, y, z over some domain, some compact domain, part of R of the real numbers cubed. The domain is maybe a block or maybe some Earth, some chunk of the Earth, or maybe a whole globe, depends. And the function values of this function are an arbitrary combination of scalars, vectors, and tensors. So in other words, the function goes from r cubed to r to the n, where then that r to the n has some semantics with it. And the most important bit, of course, is that these functions are discretized, otherwise you couldn't handle them. Generally, and in the case of the program we're looking at, you have some kind of 3D grid where data values are associated with a grid in some form. These grids might be regular, irregular, hierarchical, like in AMR. It doesn't really matter that much. And the last bit I want to mention is that these functions are typically time varying, but as it turns out, the software we have right now doesn't currently really handle time varying data very well, which is why this is not going to be treated very much in this talk, or in the seminar, I should say. Now, let's talk about the actual process of turning data into pictures and the very simple pipeline I have on top here. Now I have no way of pointing at things. I don't know if you guys can actually see my mouse cursor. Somebody give me a heads up. We start with data on the left. We use some algorithm and then that algorithm applied to the data generates a picture. Examples for those algorithms are color map cross-sections, where you do a cross-section, a 2D cross-section of your data, and then the data values are turned into colors based on some color map, and then that generates a picture directly. Another example would be an isosurface, which connects all the points having the same data value, or streamlines, which is the path of a particle through the data if you have a vector field and so forth. So the easiest way now, whoops, nope, that's the wrong button yet again. Here we go. I need to make one further distinction, of course, and that is now the interaction. In regular visualization, you generate a picture using the pipeline I mentioned, and then that is what you work with. That picture might be a printout, might be on a computer, but in other words, you're working, the picture is the product. Whereas in interactive visualization, you are actually working, you're influencing the algorithm that is generating pictures, and the pictures are just a means to an end to extract data. So the pipeline gets augmented by having the user influence the algorithm by selecting different algorithms, by setting algorithm parameters, and then generating a rapid sequence of pictures which show you whatever the current result from the algorithm is. And that turns out gives a lot more insight into the data than just looking at individual pictures. And the best way of showing that is via a movie. So I have one here. Due to the way we are sharing that over Adobe Connect, it's going to be very choppy and very low res and fuzzy. So the full resolution, beautiful movie is on YouTube. Just follow this link and you can watch it there. It has audio as well. In this case, I'm going to talk over the video. So I'm going to stop sharing this presentation now and go over and share the video and hope that that works. Hope you can still hear me. I'm going to share this. Here we go. Okay, that worked well so far, and I'm going to start the movie. And here we go. Now, this is just, I recorded myself earlier doing a session with 3D Visualizer. Normally at this point I would do a live demo, but I'm running on Windows today, so I can't do that. The video just stopped for whatever reason. Here we go. So what we're looking at here is a seismic tomography dataset that was created by Richard Allen from the UC Berkeley Seismolab, and he generously donated that for us to use for these kind of purposes. And what I'm doing here is I'm showing the domain of the dataset, which is that slightly curved brick, which is a regional discretization of the western US. And what I'm doing now is I'm creating a color mapped slice into the data, one of those algorithms that I mentioned earlier. And the trick here is that as I'm dragging the slice through the dataset, or actually I'm dragging the dataset through the slice, but that doesn't matter, you see how the slice changes. And so doing this is a very quick way of finding features of interest, like this blue blob on the top left. And I just brought up a color bar, which shows how data values relate to colors. So on the left, we have red colors for slow pressure waves. This is again seismic tomography. On the right, we have blue colors for fast waves, because generally we assume that the difference in velocity is mostly caused by temperature. And then what I did here is I just created another slice to show a very red, a very hot feature. And so now I have these two slices in my data set. And as I mentioned earlier, slices are I find a very good way of quickly finding things of interest. But what they are not really good for is showing what those things that you have found actually look like, because they are just cross-sections after all. So one way of remedying that is to make yet another slice, maybe like this one, orthogonally to the first two, which kind of gives you now two cross-sections, and if you have a lot of spatial imagination, you can kind of gather the shape of the thing from these cross-sections, but it's really kind of hard. So what we do instead is we are augmenting these slices with a complementary visualization method, namely the isosurface, which I'm going to do just now. I'm just noticing my narration now caught up with the video. Perfect. Quick reminder, isosurface is a 3D equivalent of a height line on a topo map. It connects all the points having the same data value. So in a 3D data set, it's not a curve, but it's a surface. And here we go. By clicking or by touching a point in the data set using the 3D cursor, I can extract in real time an isosurface that connects all the points having that same data value. Here we are looking at just some random background noise, and then here we are dragging back to an actual feature I want to look at. Now, a nice thing here is that this interactive feedback allows you to find the isosurface that really delineates your feature by looking for jumps in topology, like I did earlier, where at one value or one position in the data set I had this localized compact feature. If I pull it any further out, I suddenly got a whole bunch of other stuff. So that's a good indicator that there's a feature at that particular location. And here I'm looking back at, well, that's the wrong window. There we go. So the actual ISO value that I extracted there is 1.279, which doesn't really mean all that much unless you are already familiar with the data, which of course the assumption is we are not. So now to show what this thing is that I extracted there, I turned from the grid display to an Earth model. So now you see that this is a subducted slab underneath the western US, underneath the Sierra Nevada to be precise. So we just isolated from the seismic tomography dataset that old subducted slab, which is very cold material. So now let's do the same thing for that hot thing over here and extract an isosurface to get the shape. I'm doing the same thing. I'm clicking and dragging. I'm looking for topology changes, and here we go. That's a pretty decent isosurface. And now that shows me this very different looking feature that is more vertical than the other one, and also not planar, but more a blob. And what this is, forgive me for not knowing the correct terminology. I'm a computer scientist, but this is the magma chamber underneath Yellowstone National Park that's driving all the activity there. Here, I just turned both of those surfaces back on at the same time, so we can look at them. So now the next question is, what is actually the result of doing these visualizations? We are looking at a picture right now, or I'm rather interacting with a 3D picture. But what we really want to get out of this is information like, what is the position of this hole in that slab? Because we don't know. Is this a real hole? Probably not. Or is it an artifact from the data? Probably, because there were just no raw data in that region, so the reconstruction isn't really reliable there. And one way now to get that information out is to just measure the position of that hole, which I just did here, by using the measurement tool. And then I can also measure, let's say, the size of that hole by just measuring across, which is about 61 kilometers. So what I did here is just, I did some very quick ad hoc measurements of 3D positions and 3D distances. And all those things are really the data that comes out of using the software to do visualization. In other words, to really emphasize that the result of visualization here is not a picture, but is exactly these measurements I'm taking right now, which would then go into the next step of the process, which would be statistical analysis or debugging, trying to figure out quality analysis, trying to figure out where that hole came from, and so forth. Similar example here, I'm now measuring the very tip of that plume of hot material under Yellowstone. I'm doing that again for data quality analysis. This is a feature that you would know where it is located on the surface in reality. So by measuring it in the simulation, or actually I should say reconstructed in the simulation per se, I can now compare this measurement from the data to the position in real life, which gives me further insight into the quality of these seismic reconstructions. So that's pretty much it for this video. I have another one which is going to come up later. Let me just stop that before we go into it. Okay, too late. And let's go back to the presentation. Okay, now I'm going to share. Nope, wrong button. Hang on. Yeah, I'm all new to this, so I apologize for all these hiccups. Share document. Here we go. Okay, well, at least we are back in the same place where we were. That's great. So let's reiterate, or let's say go over what we just saw in this video, and let me ask a very esoteric question, if I can get to the next page here. Hang on. Here we go. Okay, before we I'm getting ahead of myself. Before I ask an esoteric question, let me just recap a little bit. The software we just saw in the video is called 3D Visualizer. It's free software. It runs on Unix likes, primarily on Linux, also on macOS, supports many grid types and data formats, but unfortunately it doesn't currently have proper support for time-varying data. And you can find a lot more information and videos about it if you follow those links I listed down here. Okay, so now let me ask my question. What is a picture? If you're looking at these two pictures I have here, the question is, are they different? And the answer is, well, duh, yeah, they are different. They are showing two different isosurfaces. These are exactly the two I extracted in the video, so there's no question here. But let's have a look at these two and ask if these are two different pictures. And yes, in one sense they are obviously different, but in another sense they're not quite, because they're both showing the exact same isosurfaces. They're just showing them from a different point of view. Now again, both of these pairs of pictures are different, but they are different in a different way. And the visualization pipeline I laid out earlier does not really explain the difference because it conflated two very important steps. So let's augment the pipeline by putting in this intermediate step where we go from data and an algorithm like an isosurface, and the result of that is not actually a picture in a traditional sense, but it's a 3D picture. There is no real good name for that, unfortunately. And so then to actually make a picture that you can look at on a computer screen or print out, we have to project it to 2D space and then generate a 2D picture. So in other words, in the first pair of pictures I showed, I used an actual different 3D picture. I used the different parameters for the algorithm. But then the second pair of pictures were the same 3D picture. They were just looked at differently by using different projections. It's a very important difference. And the crux of the matter is that projections always lie. They distort sizes and angles, and they obscure spatial relationships. You're looking at a 3D thing via a 2D projection, so it's never going to be precise. And so the next obvious question is, can we somehow visualize 3D data without projection? Just lopping off the last two steps of the pipeline, and I wouldn't be asking the question if the answer were no, so the answer is yes. So now how do we do that? Well, we can make sculptures of our data, which essentially would be a 3D picture, but of course that is rather awkward. Even if you have a 3D printer, that is not exactly real time and it's not exactly interactive. So the next better thing is, instead of making real sculptures, we make virtual sculptures using holographic displays. So let me show you a video of what a holographic display is. Again, this is going to be very poor quality. Here's the link to the full video on YouTube. I'm switching back over to the video player. Share my screen. Let's do this. Okay. And here we go. So now this video unfortunately doesn't show a 3D visualizer, but it shows a holographic display. And this is pretty much what it looks like. There's a real person there to the left. You now see only the hand. And there's a real globe there. No, I'm lying. The globe is not real. The globe is a hologram. It's not a hologram using lasers and mirrors, but nonetheless it's the same thing. It is a real image that is touchable, in the sense that if you are the person standing in the cave, you do get fully the impression that that globe is actually there. You can touch it. If you touch it, you don't feel it, just like a real hologram. But otherwise, it is a very convincing simulation. So why is that different from just looking at a picture? And the difference is that we are not actually projecting this excuse me, this 3D image. It is in the space there with you, which means that there's no distortion of sizes and angles. If something is a right angle in the 3D object, then it looks to be a right angle when you're standing in the holographic display, in this case a cave, and looking at it. Also, if two objects have the same size, even if they are in different locations, they appear to you as if they had the same size. A side effect of having such a display, as you can see here, is that it also makes interaction a lot easier, because a big part of that is that you have these 3D input devices, like that black wand-like thing that she's holding in her hand, and that allows you to navigate through your data very naturally by just, as you saw, she could pick up the globe and move it around, and it doesn't come out quite like that in the video, but it's essentially the same thing as if you had picked up a real globe and moved it around. And here she's changing the scale and again picking it up, moving it around. Here it's a little bit more obvious what's going on. The secondary benefit of these 3D input devices is they allow you, make it much easier to precisely pick locations in 3D, locations, for example, to take measurements, like shown here, or locations to create a slice or an isosurface, which is kind of awkward on a 2D screen. I'm very well trained, which is why it looked easy in the video I showed you earlier, but it's actually not. Here it is a lot easier. Now in this video it's not quite so easy for a very subtle and deep reason I'm not going to explain, but just you have to take my word for it, unfortunately. The video goes on longer, but I'm going to cut it out now because the salient bits were covered. So I'm going to go back to the presentation for the final stretch. Okay, stop sharing, share document. Okay, here we go again. Full screen. All right. Now, again, if you want to see the video in all its glory, just follow that link to YouTube. You can see it there. So, just to recap what we just saw in the video, holographic displays are a combination of special hardware and software And the main difference to what we normally think of as a 3D display is that it actually presents 3D objects as opposed to pictures. And these objects are there with you. They are real looking, they are touchable, you can interact with them, there are no distortions. And the side benefit of that is, again, improved interaction. Navigation, meaning moving your data around, is much easier, and measuring things and extracting isosurfaces or slices also much easier. So now the thing about them is, of course, that these are dedicated display environments. They are not your normal computers, which means that they cost extra, and they come in a wide range of cost and complexity. And just to give you an idea, I want to list a few real existing environment types and just give you a rough idea of how complex and difficult they are. The first one I want to mention is the cave that you've seen in the video. That's actually the high end of these types of environments. It's very expensive. The one we have at Davis is probably about $500,000, but it's also the best environment in terms of usability and effectiveness that I have ever worked with. But you wouldn't want to build one of these until you're really sure you want one. So then what we've been doing over the last few years is trying to figure out how can we provide the same functionality but at much lower cost. And one system that we didn't invent it, but we came up with is this combination of 3D TVs, the same kind you would buy at your friendly electronics store, with a tracking system to, for example, provide 3D input, but more importantly, holographic display. Here's one that I have in my lab. It's me sitting there using 3D visualizer on a medical data set. It's a CAT scan of somebody's skull, and I'm wearing 3D glasses. I have a 3D input device in my hand that is a Nintendo Wii controller, and I'm essentially doing exactly what I was showing in the cave video, but these things are much smaller and also much less expensive. Building one of these between $7,000 and $8,000 kind of depends on daily deals. The problem is you have to kind of build it yourself. We have instructions for doing that, but they are not turnkey systems. So then a new development is this ZSpace thing. This picture here is a, how can I say, marketing material. Don't trust the picture, but this is pretty much what it feels like working with that thing. You have virtual objects floating above the display. The display is much smaller than what I showed in the last slide. It's only a 23-inch monitor, or 24, as opposed to 72-inch, but otherwise it works exactly the same. You have a tracked input device, that stylus he's holding in his hand. You have 3D glasses. The benefit of this is it's completely self-contained. You can go to a store and buy this, and then just plug it in, and it more or less works. It runs our software. Quality-wise, it's about the same as a 3D TV system, but again, it's something that you don't have to build yourself. So I wanted to mention that because it is an existing solution you can just get in the store. It costs about, well, the display itself costs about $4,000. It's a bit too much for what it does, but oh well. But unfortunately, due to the way it's currently set up, you also need a special computer to run it, which is yet another $4,000, but I'm working with them to hopefully change that. And then if you have been to our, and go back one slide, if you have been to our booth at AGU, you might have seen the 3D TV system we brought there, and that is even further a step down because it is not with tracking. And I'm not listing that in this list because at that point it stops being holographic and is suddenly merely stereoscopic. I can't go into the difference there, but trust me, it's a huge difference. But again, it's much, much cheaper and easier to set up if you want to go with that. But there's yet another cheap way of doing it, and that is using head-mounted displays. And I didn't have a good picture, so this here is a still from a video that you can also watch on YouTube. It's using 3D visualizer. If you want to see it, it's actually a nice video, I think. And so the big picture is what I see when I'm wearing that head-mounted display, which is again a CAT scan of somebody's abdomen in this case. You can see the rib cage and the spinal column. And then that little inset on the lower left, that is actually what I look like when I'm doing that. So I'm wearing this thing on my head, and I'm holding these other two things in my hands, which are the input devices. And together, this creates the illusion of having, again, a holographic display. Now, you need to watch the video in order to really appreciate how that works and what it's like to use. But trust me, it works pretty well. So, oh, and in terms of cost, this is just a very, very cheap thing. You need a regular computer, and then that head-mounted display costs about $300, and that thing I'm holding in my hands is about $100, so a $400 investment for a pretty decent holographic display. Okay, I am totally out of time, so I'm going to wrap it up. Very briefly, what I was trying to get across here is that interactive visualization, the ability to manipulate your algorithms, your visualization algorithms with real-time feedback is a very effective tool for getting information out of data. Don't trust me for saying that. Trust the people who are using the software, who are using it for a variety of applications, from really doing statistics to debugging their simulation codes to understanding what data is all about, etc., and then writing papers about it. We have a whole bunch of them. They are linked on the KeckCAVES page I linked earlier. The second part is that interactive visualization works best if it's an integrated system of software and display hardware. It works on a regular computer, that's what I showed in the first video, but it really works a lot better if you have a 3D, ideally holographic display system, which costs extra, but fortunately there are multiple levels of cost and complexity that you can choose from. And finally, the 3D visualizer software that I showed is free, but it's under development. And the most important bit that's missing is proper support for time-varying data. Like I mentioned earlier, right now you can use it to look at individual time steps of a data set. You can use it to look at a selected number of time steps, maybe 2 or 3 or 4, but it's not nearly there where it needs to be, where it should be really. So yeah, that's my part of it. So at this point, I'm going to stop sharing and open it up for questions.
Thank you very much, Oliver. I don't know, we actually have more time, so I don't know if you have other videos that might be of interest to the communities that you would like to show and walk us through any other sort of data sets that might be of interest to this group.
Well, I don't, as it turns out, unfortunately, I do not have that many videos showing 3D Visualizer. So this one that I showed earlier, I just made this morning. The other one is the one with 3D Visualizer on a head-mounted display. Well, unless there are questions right now, maybe we can just have a brief look at that.
Yeah, but there's also Crusta too.
Oh, I don't have really any videos about Crusta, as it turns out. At least not with me, I think. At least not any good ones. Well, let me see. I can go through my hard drive here and see if I have that video. I think I have it with me. Let me see. Open file. Talk to myself. I'm looking for it. Okay. Here we go. Movies. Well, apparently I lied. I do not have it with me. I don't have it on this drive. Just go to YouTube and watch it there. But I do. Oh, I do have this one. This one is a good one. It's also using 3D Visualizer, and it shows another feature of 3D Visualizer I didn't talk about at all. It shows remote collaborative visualization. Lorraine, do me a favor and let me know if anybody has a question, because I don't see the typing section from here. So what we have here is, again, 3D Visualizer. You can see that Telltale Box in the middle, which is the domain of the dataset. But now you're also seeing a kind of fuzzy version of me to the right, and then to the left, that's a kind of fuzzy version of Dawn Sumner, one of our scientists.
We don't have anything.
Oh, because I'm sorry. Yeah. Yeah, I did not share that. Okay, never mind. Hang on. Oops. Okay. Yeah, sorry, here we go. So you have the Telltale Box for 3D Visualizer. You have a fuzzy version of myself to the right. You have a fuzzy version of Dawn Sumner, one of our scientists, to the left. And so what happens here is actually that we are in different places. Dawn is in the KeckCAVES environment, and I am in my own lab across the street from the KeckCAVES environment, sitting in front of the 3D TV that I showed in one of the photographs. The data set we're looking at here, the video is choppy due to Adobe Connect, I'm assuming. So again, just watch it on YouTube. I actually have a link to that in my slides. So we are together looking at this 3D data set, which is a CAT scan of a microbial community that Dawn, or one of her students rather, dug out of a lake in Antarctica during some of their fieldwork. So what's happening here is that both Dawn and I are mapped into this shared virtual space as, again, virtual holograms. So we are there in 3D. We are mapped into the data space, And what that means is that essentially it's pretty much like having a face-to-face conversation and working with a sculpture of the data. You see how Dawn is using her hand to point out features in the data. She is seeing this brick of stuff floating in front of her, so she just in the cave walks up to it and touches it with her hand, and then I can see and you can see her 3D hologram touching the data in the exact spot where she touches it, even though we are in different places and not actually in the same space. And I'm using my finger to point at something, and then Dawn again goes in with her finger and explains what it is. So this is sort of the next best thing to being in the same environment and having a face-to-face conversation. Oh, Gerald is asking why there's a difference in size. That is an excellent question. What happens here is that if you go back to the video I showed earlier of my wife, it was actually my wife in the cave playing with the globe, you saw her scaling the globe to different sizes. And when you scale data in the cave, you're not actually making the data bigger or smaller, you're making yourself bigger or smaller in relation to the data. So if you're zooming into the data, you're actually making yourself small. Think of it as the Alice in Wonderland effect. I think Louise came up with that metaphor. And if you're zooming out, you're making yourself bigger. So if you're in the cave by yourself, you can't tell the difference because of relativity. If you're making the data bigger or yourself smaller, it has the exact same visual effect. But if you're working with someone else, then you're actually seeing that. If I am in my environment and have this data set in front of me, let's say, about the same size as I, and then someone in a different environment zooms in, then they see the data getting bigger, but I do not see the data getting bigger, I see them getting smaller. It is a kind of, it sounds weird, but it's surprising how intuitive it is and how well it works. It is not weird at all if you're actually doing it. And the same thing is true with orientation. You're noticing, or you might have noticing, now we are standing next to each other. And earlier we were not standing next to each other, we were standing on other sides of the data set. But we didn't actually move. We just picked up and moved the data. Again, when you're moving the data, you're actually moving yourself. And so by freely orienting it, you can essentially put yourself into any arbitrary position, orientation, and size. What that means is, if I were to take the data set and flip it over upside down, then Dawn would see me suddenly floating upside down in the cave, which again sounds really weird, but surprisingly it's not weird. I don't really know why it's not weird, but it isn't. Actually, I should mention what we're doing here is we're now using yet another analysis tool to sketch out the skeleton, so to speak, of these microbial structures just by drawing freehand in 3D, which is something that you really can only do in a 3D environment because you need to be able to really touch things in 3D. And we're doing it both. I'm using red, and I think Dawn is using a different color. But yes, this is something that I didn't mention in the talk because it's not really pertaining to visualization itself, but rather to collaborating on data. The idea here being that you can really have people working with the same data set in real time over long distances without having to have them be in the same place. So as part of this, we are currently building sort of a network, and here Dawn is rotating the data and just floating up to the top of the screen. Again, it's not weird at all if you're actually doing it. It's funny how that works out. Okay. Let me go back to the webinar pane to see if there are any more questions. Well, so far not. Bill is typing. Right, what other things have we done in the cave? Well, plenty of things. I'm not really on top of everything that's going on, to be quite honest. Let me think. The example that I showed you in the first video was seismic tomography reconstruction that was done by Richard Allen at UC Berkeley. Richard came to us with his data, we looked at it, we figured that we could probably help him analyze these better, so he came to the cave and started working with it, and then he came a couple of times to do analyses and bring in new data sets, and then at some point he was tired of driving up So we built him one of those low-cost versions. Actually, he built it himself, one of those low-cost versions for his own lab. So he has that right now. Then, as Louise just pointed out, LiDAR visualization is a huge chunk of cave time. Didn't talk about LiDAR at all, but go to the KeckCAVES homepage and check under LiDAR to see what we're doing there. We have software similar to 3D Visualizer, which can be used to look at massive point clouds, which are gathered by remote sensing using laser scanners. What it means is we reconstruct those point clouds into very detailed models of the Earth's surface, for example, and can then do virtual fieldwork in the cave. In other words, making maps, measuring size and location and distances between features, displacement during earthquakes, faulting, what have you. Concrete applications we've done were scientific response to the 2010 Haiti earthquake, where we used a combination of LiDAR viewer and Cruster, yet another piece of software, to look very detailed at the topographic data from Haiti that was gathered at the same time. We did the same thing in response to the 2010 Baja California earthquake, where we actually collected LiDAR data ourselves and then did a lot of field work. Well, our students did a lot of field work in the cave, got some very good data out of that, which led to some very nice publications. So that was LiDAR. So then in terms of 3D Visualizer, what else have we done? We have done geodynamics work. We have done a lot with the subduction simulations. One of our faculty, Magali Billen, and one of her former students, Margaret Geodynamics, have used the software and the cave to debug and create a very detailed model of the Alaskan subduction zone, which led to a very nice paper. Oh, I just saw that there's a question here. You showed some images which had global topography. Can these be imported in real time using the macOS version of the software? That is, does your software know where to find global topography? Let me answer what I think your question is. The software does not automatically go out and get topography data. In this particular case, the data set that I loaded in, the regional seismic tomography data, it knows that it is a chunk of the globe, so it also knows where it is on the globe. So Visualizer has this way of bringing in a model for the globe, which is where the color came from. And the data source for that is the NASA Blue Marble dataset. So yes, you can bring additional data into 3D Visualizer, but it's not an automatic process. You have to essentially combine and assemble these data sets yourself, which is not really that difficult normally. If you know where your data are in a global context, then it's almost automatic. But depending on what you bring in, it takes some effort. To give you a concrete example, Lorraine mentioned in the introduction that students of ours participated in the geothermal energy competition. And so the project the students actually did was to download a whole bunch of different data sources and combine them all using 3D Visualizer again to do a comprehensive visualization. So the data sources they got were a detailed topography model, satellite and aerial photography to drape over the topography model, which was of the Valles Caldera geothermal energy field in New Mexico. And then they also got seismic profiles and other cross-sections, which they scanned from publications and then draped into the 3D data at their proper spatial positions. So in other words, the cross-section of the surface on the seismic cross-section matched the topography in the dataset and so forth. They brought in seismicity data, they brought in well logs and so forth, and were able to create and combine all that with the temperature distribution dataset in order to then be able to really understand the structure of that particular geothermal energy field. And they did such a nice job that they won the competition, which was really great. And yes, Bill, to answer your second question, that's correct. You would bring in Blue Marble, georeference it with your volume, and you're pretty much good to go. Yeah. Let's see. Oh, Louise brought up the point of museum outreach and education. We have also worked with science museums, specifically with the Tahoe Environmental Research Center up at Lake Tahoe, with the Lawrence Hall of Science, and with the Echo Lake Aquarium Science Center in Vermont, to use our software for the other use of visualization. I didn't mention that I should have. Visualization typically has two uses. One of them is data exploration, data analysis, which is what I was talking about the entire time. And the other view, of course, which is probably more common at this point, is communication of results. In other words, you know what's in your data, and now you want to make the perfect picture to explain that to someone else, for which visualization is also very powerful. But it's a fundamentally different use, because then the picture really is the end product. So for this museum collaboration, we really went across the watershed, so to speak. No, well, actually, yeah, pun intended. And created more traditional visualizations, meaning 3D movies, interactive 3D displays that can be shown on 3D screens that we did install or are in the process of installing at these museums, so that they can either just show the movie or do a live guided tour to audiences, flying them through a 3D data set, showing different features of interest, measuring them, and so forth. For that, we primarily use LiDAR viewer, Cruster, but we also are using 3D Visualizer and other KeckCAVES software to look at, for example, temperature distributions in Lake Tahoe, or the internal mixing in the lake, and things like that. This is all work in progress, but that's excuse me. That's where we are going to go with that. I think that's a pretty good overview. So KeckCAVES is really this central facility that we have, but it goes way beyond being just a visualization environment. What it really is a project that is aimed at developing new techniques and technologies for data analysis, which means we are developing all the software that you saw here and that you can get from the webpage. We are developing all these new approaches in very close collaboration between the computer scientists and the well, earth scientists, physical scientists, geologists, anybody who would use these data. And then once we have those software, we can then push it out to other people. So we are collaborating with a lot of people here on campus. We are collaborating with our med school, which is off campus, technically speaking. Lorraine just asked about other groups who are using the software. That is an excellent question. I don't really have an overview. Our software being just freely downloaded from the website, we do not know how many people have downloaded or using it. Based on the kind of questions that I get and feedback and seeing it pop up in places here and there, it's probably several hundred people who are using it. 99% of those are using it just on a desktop, so they don't have any really holographic or 3D display systems, but there are a few. As I mentioned, Richard Allen at UC Berkeley has a low-cost 3D TV system, which he's using specifically for seismic tomography data analysis. As part of another project on paleoceanography, we installed two systems, one at UC Santa Barbara in the Geo department, and one at the Woods Hole Oceanographic Institute on Cape Cod. Unfortunately, those two are not working right now. They had some serious trouble due to renovation work in the building, so really physical problems, and we are trying to figure out right now how to fix these things remotely. As I mentioned, these systems are do-it-yourself and build your own, so if they break, you need to know how to fix them, and unfortunately in those two cases we built them and now we have to teach them how to fix it. Who else has? Let me think. There are people here and there who are using the software in VR environments. Idaho National Lab is one group. University of Illinois is another. Let's see, Virginia Tech is another, but they are using it for a very different purpose. They are computer scientists and are using our software to study visualization itself. So they're actually using it to do science, but for them, visualization is the science. They're doing user studies and usability and so forth. But they have the software installed and running. That's all the places I can recount off the top of my head where people are using our software in a real 3D environment, meaning where you would like to go and see it, because there's no point in going to see somebody using it on a desktop because you can download it yourself. Yeah, I really can't think of any others right now.
Oh, Jerry said USGS.
Oh, I completely forgot. Of course, Gerald is using. Sorry, Gerald. Gerald is using LiDAR viewer in his office at USGS Sacramento. Gerald is using a non-holographic 3D display system. So in other words, a stereoscopic screen. I think Gerald is using a projector correct me if I'm wrong, and just normal input devices, mouse and keyboard for interaction. So it is a little bit better than just a 2D screen, but it is not as effective as having a true 3D environment like the cave or the others I showed. And yes, Gerald is primarily using LiDAR data. I should mention that Gerald is actually the reason why we developed LiDAR View in the first place. Because many years ago, he came to Davis and did a presentation about the then new technology of terrestrial LiDAR. And I saw the presentation and I thought that, wow, we could really do something with this. And so then we went ahead and developed the software. And now it's, as Louise mentioned, it's probably one of the biggest ones that we have, because LiDAR data has completely transformed, or is completely transforming the way Earth science is done. And it's very, very difficult to deal with normally, unless you have LiDAR Viewer. And so that's why we are very happy with how that turned out. As far as I know, LiDAR Viewer is really the only comprehensive software that allows you to work with massive LiDAR data sets and really do scientific data analysis in the sense that I was talking about in this webinar.
Great. Jerry's still typing. While Jerry is typing, I would just want to again thank Oliver for his time today and showing us what can be done with 3D visualization. Next month, we are going to have another talk on visualization. It's going to really take us into a totally different realm. Oliver took us into a literally different world. This is going to take us into a different realm of exascale class visualization. Our next webinar will be on February the 13th at 2 p.m. and it'll be with Professor Hank Childs. It'll be entitled Exascale Visualization, Why Things Will Change for You. So as always, more information on all events can be found on our website at geodynamics.org, and we will also be posting a video of this webinar there as well. Oh, Jerry has one more question. Oh.
Nope, just a comment. Thanks, Gerald. I appreciate that.
And thank you, everybody, for joining us today.
Yes, thank you for joining us. And I'm signing off. Bye-bye. Oh, there's one more thing.
Yep.
You're welcome. All right, now I'm signing off.